Hello friends, welcome to TechCube GATE classes. My name is Professor Vivek Singh Rathore and I am Assistant Professor at Government Engineering College Bilaspur, Chhattisgarh, working as a TechCube faculty there. And I am teaching Signals and Systems in this GATE classes. And we have completed almost Module 1 and 3 lectures of Module 2 also. In Module 2, we are discussing continuous and discrete LTI systems and what are their property and how can we calculate the response of a system. So I think in first and second lecture I have completed discrete time LTI system. I have completed almost all the method how to calculate the response of a discrete time LTI system, and in the last lecture I have completed how to see graphically or how to calculate graphically the response of a continuous LTI system. So one more method was there which was left, and that is mathematical method, means by formula only we can calculate. So sometimes there are questions which are not in the graphical form and they are asked to calculate the response of a system. So how can we do it in the continuous time system? We'll see it. So let's see it. We'll start with some questions. We'll write with some questions which we have not discussed in the last class. Like if you have been asked for performing convolution between sine t into ut convolution with, let's suppose, ut only. Okay, you have been asked to convolve these two signal and get the output response. What is the output response of the signal? So see, this is your input, and let's suppose that your impulse response is, let's suppose, this. Okay, so now how can we do it? For calculating the response of a system, what you need to do, you need to just integrate minus infinite to infinite, and both signals for domain you need to change. First signal domain you change sine tau u tau, and second signal what you need to do, you need to reverse it and then shift it. So you can write it u t minus tau, and the value will be d tau. Okay, so this you need to calculate. Very easy it is actually. See, u tau into ut minus tau. Actually, whenever a signal is multiplied by ut or u tau, means it is now starting from t is equal to 0 or tau is equal to 0. Okay, but first we need to see that sine tau is multiplied by this two signal multiple. So what this two signal signifies? See, when if you'll plot u tau, you'll see this is the domain tau and this is your signal. It is going on. Okay, it is going on. This is your u tau, let's suppose. Okay, and if you want to see ut minus tau, you'll get here, see, this is tau, and let's suppose this is here. So ut minus tau means you'll get from here it will start, because u tau will reverse it and then you will shift it. Let's suppose till some value you have been shifted, up till here you have been shifted, because t is, let's suppose, this much value. So, and it is going on till minus infinite. This is your u t minus tau. You can understand, because see how to plot it, you must be knowing. I have told you in first module also. U tau and ut minus tau. So first you will change minus tau and then you will shift till t values is there. Now you need to, what you need to do, first you need to multiply this two signal. You need to multiply. So obviously this signal is there, this signal, the value is 0 in minus side, and here some value is there. 0 into some value, it will cause 0 only. So final output I am plotting here. Tau is there and this is your base 0 value. So in the negative side nothing will come, because anything multiplied by 0 it will come 0 only. Anything multiplied by 1 it will come same value. So till t value it will be there. So this t value, 0 to t value, it will be there. So definitely you can understand that u tau into ut minus tau will consist of a pulse signal of 0 to t range. Okay, this is your u tau into ut minus tau. Definitely. So obviously any signal is, if you multiplied by this type of signal, it will be exist only in this duration only. because after this anything is multiplied by 0, it will come 0 only. So what you need to do, if you are integrating from minus infinite to infinite, this is of no use. So you can write here as minus, not 0 to t, because overall signal whatever may be will be multiplied by this, it will exist only from 0 to t only. So it will exist from 0 to t only, and it will exist sin t, and d tau, because the value is 1 only. This value is 1 only. So sin t into sin tau, sorry, I think sin tau into d tau, because see, sin tau was there. Okay, sin tau will be there. So and integration for sin tau, you must be knowing that when you integrate sin, it will come minus cos of tau. Okay, and you can do 0 to 2 t, so you can do minus of cos of t minus cos of 0 is 1. Okay, so you can write here as 1 minus cos of t, and this is for for t is greater than 0 now. From 0 to t you are taking, so you can take as ut. Okay, so this is your output. So how we are calculating the output? You have been given a signal sin t into ut, conversion with ut. So what we have done, actually we have done minus infinite to infinite, your first tau, and then t minus tau. If you have remembered the property, whatever signal is multiplied is convolved with ut, it is generally represent the integration also. So minus infinite to t sin t into ut also you can do. Okay, and dt, and there also ut is there, so you can do from 0 to t sin t dt, and there also you can calculate the same value what we are getting. So what I have told you earlier, that is also verified from this question, that any signal is when convolved with ut, that is same as integration of from minus infinite to t dt. Okay, that signal. Okay, let's do it for another question. We'll solve one more question, then maybe you will be more comfortable in this type of convolution. So what we'll do, we'll take one more value, like your input is given as e to the power minus t into ut. This question is given, and let's suppose some other signal is given. Let's suppose ht is given, e to the power minus t into ut, same. Okay, both are same, and now you need to calculate output. What you will do, so you know how to calculate output. It's very easy. No need to panic for convolution. You just need to do what, equal to minus infinite to infinite. Input is there, you just change the domain, e to the power minus tau u of tau. Okay, next whatever ht will be there, you need to change the domain from t minus tau, first tau, then reverse, and then shift. So e to the power minus t minus tau. Okay, and u t minus tau, and there d tau. Simple, nothing we have done more. Now we'll solve again. See, e to the power minus tau is there, and e to the power minus plus, e to the power plus tau will be there. It will be automatically cancelled. Okay, so no problem is there, we will cancel it. Main problem is e to the power minus t will be there, but it is overall d tau, so e to the power minus t will be constant, it can come out. E to the power minus t you can remove outside also. Minus infinite to infinite, u of tau will be there, and u of t minus tau will be there, d tau will be there, else everything is outside. Now only you calculated u tau into ut minus tau will be a pulse signal from 0 to t. Just only we have calculated now. U tau into ut minus tau, output is like this. Okay, so you can put here e to the power minus t 0 to t into 1 value is there, and d tau will be there. So directly you can calculate here, the value will come t into e to the power minus t, and this is from 0 to t, so you can write ut. So this is your final output of a signal. You can understand that how we are doing it is if a question comes like this and you have been asked convolution, just in fraction of seconds you will get your answer very easily, and you just need to do what, just change the domain, and you need to integrate. Nothing is more than that. And if you have been asked for some graphical signal, these type of signals are there. If same duration is there, pulse signal, you need to get triangular pulse. If it is of different duration, you will definitely get a trapezoidal pulse. And if it is not like this also, if it is not standard questions also, if some different type of questions are there, then also what you need to do, just you need to do um, meanwhile you can do differentiation. By differentiation method also, you can, if you are able to do differentiation of one signal, which will be easier for you to then multiply and then you can integrate it, then that method is also easy. Otherwise, just no need to do different types of thing. You just do form the graph. You first signal will be in tau domain, second signal will be in t minus tau domain, and means tau, and then shift to t, and then just multiply it and then add it, so means integrate it, so you'll get the final output like this. So these convolution are actually easy, not very much difficult if you see. And then okay, I think we have already seen so much method for convolution. I have told you at least 4 method in discrete time LTI systems also. So let's see some properties of LTI system. LTI systems have different types of property, so we'll deal with some properties of LTI system. So let's get started. uh, properties of continuous time LTI systems. So there are some properties which can be asked in objective questions also. So you should understand it more briefly. See, first property, if you will see, first property, write with yellow. First property, if your ft is convolved with h of t, you are getting output as, let's suppose, y of t you are getting. But let's suppose that your signal is time scaled. Let's suppose this is f of at is there, convolution with h of at. Let's suppose both are time scaled. Okay, so what we'll get, we'll get here as 1 by a, 1 by a will come here, and you'll get here y of 80. Okay, so this is your first property which you need to see about, that whenever a signal, okay, whenever a signal is time scaled, and your impulse response is also time scaled, so you'll get output as, with the same scaling factor, you'll get output as, your scaling factor will come as 1 by, and your output will be also time scaled by a only. Okay, this is time scaling property of convolution. And this applies for reversal property also. Like see, second property we can write here as y of let f of minus t will be there. Okay, f of minus t is convolved with h of minus t, means whatever f of t and h of t is there, if you reverse it, then also you'll get output as 1 by scaling factor is 1, so scaling factor will be 1 y of minus t. This applies for time reversal also. Okay, so now you can understand that what if a is positive, let's suppose that if f of 2t will be convolved with h of 2t, or f of minus 2t is convolved with h of minus 2t, the output will be 1 by a only, so 1 by 2 only. But in the first case output will be y of 2t, in the second output will be half y of minus 2t. So this you need to understand that a may be positive or negative, whatever your scaling factor is there, here the value is always positive, so you can also write it as 1 by mod a. Mod a you can write it. So after seeing the time scaling and time reversal, we'll see time shifting property also in our convolution or response of a LTI system. So we'll see, I think it is the second, and we'll see the third property. Third property is time shifting. So if we are doing time shifting in with same t with, for input also, and let's suppose you're doing some time shifting in your impulse response. So what output you will get? So output, if your ft convolution with h of t was y of t, then if it is done t minus t1 and t minus t2, then what you will get output as yt minus t1 minus t2. Okay, this you need to see, practically I will tell you. See, if your signal is there, this value was there, 0 to, let's suppose 2 is there, and this is also, let's suppose 0 to 4 was there. Okay, and this signal was the output of, if we are doing convolution, we'll get output as from 0 to 2, from 0 to 2, and then from like this 6 2, and this will be 4 6. Okay, so this was your output earlier, but now if we have shifted the signal as, let's suppose this is 2 to 4 convolution with, okay, this is, let's suppose this is 5 to I think 9. Okay, what output you will get? You will get output as, see, from 7 it will start 7. Okay, it will start 7. I'll plot, I think I'll plot here. 7 it will start. Okay, and 9 plus 4 11, it will go 2 7 9, and 11 to, I think, no, I think 2 and 4 6 is there, so 7 3 10 13 will go, and it will be 11, like this. So this will be there. So see, you can see the output as overall output has been shifted from 6 to 13, means 4 plus 3 7, and here how much it has been shifted? It has been shifted from, I think, 2 value here, for 2 value it has been shifted in the right hand side, and I think it has been shifted 5 value. Okay, so 5 value here, from 4 to 9, 5 values have been shifted. You can write it like this. Actually, if it is ft, so it is your ft minus 2, and if it is your ht, it is your, this signal will be h of t minus 5 will be there. Definitely it will be there. So output will come, if it is output, if convolution of this will be yt, so output will be coming as yt minus 5 plus 2 7, t minus 7. So obviously this, your yt was there, this has been shifted here, and how much it has been shifted? 7 it has been shifted. So definitely from this time shifting property also you can solve many questions like this. So this is the third property which I was telling, after time scaling and then time reversal. Now we'll see some other property, like what are commutative and what are associative and distributive property. So we'll talk about first commutative property. Commutative property. Actually, what is commutative property means? See, whenever a signal is multiplied by another signal, if it is same as for second signal multiplied with first signal, then the system or whatever you are doing, the operation we are doing, that is following commutative property. So whether our systems are following it or not, LTI systems will check it. Let your input signal is ft, if it is convolved with h of t. Let I am telling you that if your input is your ft and your impulse response is your h of t, if it is convolved and you are getting output as like this, so whether if you will reverse it, whether if you are giving input as ht and your impulse response is like of ft, whether you will get same output, that is actually commutative property, and it is true. It is true, both will be equal. Okay, so whether you are doing f of t convolution with h of t, or you are going for h of t convolution of f of t, the order may be changed, the value will be remain same. Okay, so there is no effect on the response of our LTI system, even if the position of input and impulse response are interchanged. Okay, so this satisfied for the differentiation property also. Like for y of t, we were doing f of t convolution of h of t, And if we are applying differentiation property, means if we are doing f of t convolution with, let's suppose, dh of dt by dt, so we are getting dy of t by dt. This we have seen earlier. Now we can do like this also, df of t dt into convolution with h of t, then also you will get dy of t by dt. So you can do either of that, or you can do like this also, df of t dt convolution with dh of t dt. If you are unable to do for one, and you are getting output by differentiating both signal, no problem, you can do like this also, d2y by dt square. So you'll get the same thing as it is. So this is actually a commutative property. We can do interchange also, and you'll get the output. Now we'll see distributive property. What does distributive property means? So we'll see distributive property. Okay. Distributive, the name suggests it is distributing it. It is distributing it. So actually distributive property means that whenever a signal is multiplied by some signal which are adding, so we'll get as a into b and a into c, like a into b plus a into c. This you have studied in mathematics also. This is distributive property. So in convolution, what we are going to see, if your ft is convolution with some addition of two signal, let's suppose impulse response is h1t plus impulse response is h2t, and then it is following absolutely distributive property. So ft convolution with h of h1t and plus f of t convolution with h1t, and plus f of t is convolution with h2t. This will be very much true. So our LTI system do follow distributive property. It means that let's suppose this is your f of t input. Okay, this has been given to both type of signal, so we'll take input as both. Here we will give this ft to both system. Let's suppose h1t will be there and this is h2t will be there, and if you are getting output as f2t, whatever your output is getting, you'll get output as, I'll write with white color, f of t convolution with h1t. Okay, and let's suppose from here you are getting output as ft convolution with h of 2t. Okay, now if you are doing summation, let's suppose here summation is there and you are getting output as y of t. Whatever output you are getting is equivalent to if you are giving input as f of t and you are taking as here summation h1t plus h of 2t, and if you are taking output as y of t, means here what we are doing, you are doing f of t convolution with h1t plus h2t. It is absolutely same as that of those type of signals. So from this we can conclude that whenever the systems are LTI systems are connected in parallel, these are connected in parallel only. So whenever systems are connected in parallel impulse response, so we can add those impulse response and we can make an individual block of that impulse. So this by this property you can solve many block diagrams in control system also. You must have solved many. You have seen that it happens then when two parallel signals are there, two blocks are there in parallel, we can add it. So actually this is the reason why we do it, because our LTI system follow distributive property, so it do like this. The same is like that of associative property. So we'll talk about associative property also. Associative property. Associate means to associate with something. Okay, so let's suppose a signal is multiplied by two signal which are also multiplied with each other. So you can also do like this, when it can associated with this also. So A into B, and you can do like this. That is called associative property, where one signal can be associated with any other of the thing. So how we can see in LTI system, I'll show you. See, if your input is there, let's suppose ft is your input, and you are passing this with a block impulse response, let's suppose h1t will be there. And now if you have been passing through it again another type of block, and it is having impulse response, let's suppose h2t is there, and then you're getting something, let's suppose another block is there h3t, and then you are getting output y of t. So here what you can say that ft is actually convolved with h1t. Okay, it is convolved with h2t, it is convolved with h3t. Okay, so and you are getting output as y3t yt. Okay, so it can be associated, you can also do like this also. Okay, no problem. So it can be associated with someone else also. So how we can do it, like, see, this is actually a convolution. So we can do, we are giving input as ft, and we can do like this, h1t convolution with h2t convolution with h3t, and a single block, and you can pass it. Okay, so what does it conclude? It conclude that whenever any number of LTI systems connected in cascade, these are all are connected in cascade, they were connected in parallel. Okay, these all are connected in cascade, and any number of LTI systems when connected in cascade, okay, can all be combined into a single system whose impulse response is a convolution of all the individual response. That is the simplest thing which we can do. So in the simplest, I'll tell you in Hindi also, कि जब कभी भी दो सिस्टम्स को पैरेलल में लगाया जाता है तो आप उसको सिंपल एक सिस्टम में कन्वर्ट कर सकते हैं दोनों का एडिशन लेके, और जब कभी भी सिस्टम्स को कास्केड में लगाया जाता है एक बाय एक लाइन से, तो आप उसको लगातार कन्वॉल्यूशन कर सकते हैं. ठीक है, सो दिस यू कैन do. This is called as associative property, and many times in control system many questions have been asked from this type of thing, and they are solved like this only. We can put in a common block diagram. Okay, so now we need to see that we have seen the impulse response of a continuous LTI system, we have seen the response of a discrete time LTI systems. Okay, so there are, we have studied in our module 1 that there are many type of systems like stable and unstable system, causal and non-causal systems, and dynamic and static systems. These all we have studied, and we have studied that how do they work, and what how we can identify that it is a stable or unstable. But there I have not told you one more method. I will tell you here that how to check a system is stable or not, or static or dynamic or not, invertible, non-invertible, by seeing the impulse response, because that, at that time I have not taught you what is impulse response. So see, after seeing the response of continuous LTI system so many, now from impulse response we need to check that a system is dynamic or non-dynamic, causal or non-causal, stable or non-stable. So we will study now with respect to impulse response. So we'll see for first static and dynamic system. So we'll check it. Let's see, by seeing impulse response or by observing impulse response, we'll see a system is static or dynamic system. Okay, so see, you have been given an input. Let's suppose this is your input, and you are getting an output. Let's suppose that you are getting giving input as x of t. Okay, and let's suppose your impulse response is h of t. Any impulse response is there, and if you are getting output as uh, as ultimately you'll get xt convolution with xt, that you know. But if you are getting output as a of x of t, then it means that the system is what they are doing. The impulse response is something, but if your impulse response is, let's suppose your impulse response is a of delta t, okay, it means that whenever a signal is convolved with a of delta t, automatically it will acquire the value of x of t and a will be multiplied. Or in discrete time LTI system, if your impulse response is h of n is a of delta of n, if your impulse response is like this type of system, then you can say that your system is absolutely static system. It means it is not doing anything, just it is multiplying with a magnitude a, and it is giving the same input as your output with multiplication of a. So this type of systems are called static system. So by seeing the impulse response like this, if you are seeing the impulse response like this, you can definitely say it as a static system. Okay, now we'll see for another type of system or another type of classification, that is stable or unstable system. So which systems, by seeing the impulse response, which systems can be said as stable or unstable system, we'll see it. Okay, we'll do it. See, if you are giving input, if you are giving input as x of t, and there is a impulse response, let's suppose h of t is there, and you are getting output as y of t. Okay, now what we are doing, output what we are getting, earlier what we used to do, that for a stable input, stable input means your magnitude is stable, means your xt magnitude is finite. Okay, is finite. Yeah, for a stable input. Okay, for a stable input, if you are getting a stable output, or not stable input, if you can say for a bounded input, if you are getting bounded output, let that mean, it means y of t is finite, then you were about to say that your system is stable. Okay, this you know. Now what is happening, xt is actually convolving with h of t, है ना? And we are getting output as y of t. uh, Actually what we are doing, we are doing x of tau h of t minus tau d tau, we are doing, that is why we are getting output as y of t. This we are doing. So ultimately what you are about to say, that for a system to be stable, your this value, this actually this value, or this convolution or total output, okay, your total output, or if you say this value is going to be less than infinite value. This is actually what we were about to say, that for a bounded input or for a bounded output, for a bounded output, uh, uh, that is only stable now, we are getting output as bounded for a input bounded. So for this bounded means this magnitude should be less than infinite, that means infinite, that means this product is also should be less than infinite. If we apply Schwarz inequality law, so we can apply that if magnitude is, let's suppose your ft into gt is multiplied, okay, and we are doing magnitude, it can be said as if f of t and multiplied by magnitude g of t dt. This is actually Schwarz inequality, we can apply here also, so we can do it like that. uh, it means that, see, uh, it can be done like this. I'll tell you, I'll write it. Minus infinite to infinite is there, we can tell x of tau h of t minus tau, है ना? And sorry, and d tau, this is there, and this should be less than infinite value. This we now we know. So now the thing is there, if this is finite, okay, and for a finite input we are getting if finite output, then that system is stable. It means that this needs to be checked, because if this is finite and if it is multiplied by some infinite value, then ultimately value will come infinite only. So this value needs to be checked. So ultimately the value is minus infinite to infinite, because ultimately if you are getting if you are giving stable input or bounded input, and if it is not bounded, then your system will make output as unbounded. So ultimately your h of t minus tau d tau will be less than infinite. This value should be less than infinite. That is the main point. Or we can say that these signal are actually the shifted one. So you can also say that ultimately from minus infinite to infinite, if you say h of tau d tau, or if you are not comfortable with tau, if you can say your h of t dt, okay, this is mod value, this value should be less than infinite value. So ultimately whenever you have been given a impulse response, and if you want to you have been asked to calculate whether this system is stable or not, just try to integrate the magnitude value of that ht, and if it is less than infinite, then that system is stable, otherwise unstable. For a discrete time LTI system, you can do what you need to do. You need to just add the impulse response magnitude, whether it is in time domain, so integrate, or if it is in discrete time domain, so you will some value, okay, and this value should be less than infinite. Okay, this value should be less than infinite. This is the main criteria for checking a continuous time signal is stable or not, by seeing its impulse response, its impulse. So the final note point what I need to tell you, that a continuous time LTI system is stable only if its impulse response is absolutely integrable or absolutely summable. Okay, for a discrete time, it should be absolutely summable, your impulse response. And if for continuous time LTI system, it should be absolutely integrable, then only your system is said to be stable system. I'll tell you one example. Let's suppose one example is there. Okay, example, h of n value you have been asked, you have been given 3u of n plus 5 is there, let's suppose. Okay, and minus 5u of n plus 2 will be there, let's suppose. Minus 3u of n minus 1 will be there, and minus 2u of n minus 4 will be there. This value is there, and you have been asked that is it a stable system. Then how you can calculate it? You can see, uh, if you have been given impulse response and you have been asked that it is a stable or not, just you can plot it. You can plot it and you can see it, and without plotting also you can tell answer, but I'll tell you first. You will plot it 3un plus 5. So for 3 n is equal to minus 5, value is 3, and minus 5 un plus 2. So 3 is here till 2 value. This is n is equal to minus 2, and then it will un minus 1, it will again it will decrease. I think it will decrease. Minus 3 will be there na. So minus okay, so minus 5 minus 3 will come. So minus 3 will come, un minus 1 means for n is equal to 1, it will again decrease. Okay, how much it will decrease? Till minus 3 value it will decrease. So it will come till it is minus 2, so it will come minus 5 here, and it will go on like this. It will go on till when n minus 4, it will again decrease. So it will again decrease for n is equal to n is equal to 4. N is equal to 4, it will again minus 2, it will decrease. So it will again decrease, and it will go, this is minus 7, and this will go on like this. So this is your actual signal which we have got here, and you can see that this signal is definitely not absolutely summable. This is just going on value. This is not summable value. So definitely you can tell that this hn is definitely not stable value. Okay, this value actually I have not I have actually one mistake I have done. This I have plotted with time domain actually. You can for n you can write t, or you can plot like this, like this value, like this value you can do, and you can plot it. I'm really sorry, I have plotted like this, or you can do ut also you can write, and then this value will be right. So this value is there, and rest you can understand that this is not absolutely not integrable. That is why this signal is not stable value. Okay, so I'll tell you one more example. I'll tell you with one more example. Let's suppose this question you have been asked that your h of t was given e to the power at u of t. Okay, and your question is there e to the power, let's suppose bt is there, u of minus t will be there. Okay, and you have been asked that this system is stable only if, your question is there, this system is, this question has been asked in GATE exam also. So this system is stable only if, when it is stable, and four options were there, that a is positive, okay, and b is also positive, and a is positive, b is negative, and a is negative, b is positive, and a is negative, and b is also negative. Four options are there. You need to solve this question. See, e to the power at u of t, first of all you need to understand that if any system impulse response is there and you have been asked for stable, you need to check that is it absolutely integrable or summable. It is in time domain, so integrable. So let's do it, if it is integrable or not. So we'll check minus, from minus infinite to infinite, if we'll do e to the power at u of t plus e to the power bt u of minus t dt, is it value is less than infinite. So we'll check by plotting a graph. Let's suppose e to the power at ut is what, e to the power at ut, you can plot e to the power at ut means like this. This is your e to the power at u of t, and e to the power bt u of minus t will be there, e to the power bt u of minus t. So see, e to the power bt is like this. Okay, this is your e to the power bt u of t, but it is absolutely negative sign. U of minus t will be there, and it is plotted like this. So we'll do it like this, like see, if you don't know to plot e to the power bt u of minus t, just you need to multiply two signals. E to the power bt is like this, e to the power bt. Okay, means it is going on, maybe like see, not like this. Let's suppose it is going on like this value. Okay, this value is e to the power bt ut, and u of minus t will be there, u of minus t will be, u of minus t will be there. So whatever in this portion multiplied by this portion only will remain. This portion multiplied by 0, it will come 0 only. So it will be like this only. This value we can say like this. Okay, so this value is there, and if it is u of t also, it will go on increasing. So this is your e to the power bt u of minus t will be there. Okay, okay, so see, this signal, if you see, if a is positive, if you'll take a as, if you'll take a as positive, then what will happen, e to the power at will go on increasing, and it will not be integrable. It will be non-integrable, and it will reach value till infinite. So a cannot be positive, that you should understand. If a is negative, so what will happen, e to the power minus at will come, and this graph will go on like this, decreasing. So this value can remain e to the power at, for negative value it can be survived, and rest for e to the power bt u of minus t is there. See, if b is positive, so what will happen, it will go on, it will remain the same. E to the power bt u of t, u of minus t is like this graph only. So it is actually value is from minus infinite to infinite. It is value is closing here only, na? So it is integrable, no problem is there. But if you are doing b is equal to negative, what will happen? See, if for b is negative, e to the power minus bt u of minus t, how it will be plotted? See, e to the power minus bt ut means it will be like this, okay. And okay, and what we are going for u of minus t. U of minus t will be there. It is actually e to the minus bt graph, and for u of minus t it is u of minus t. If we are multiplying both signal, what we will get? Only this value will stay. This value will stay. So this value is going on till minus infinite. This value can be infinite value. So this is also not absolutely integrable. So we will not prefer here negative value for b is equal to negative. So b is equal to positive. So ultimately your answer can be a should be positive, a should be positive, and b should be negative. A should be positive and b should be negative. Your b option will be satisfied. Okay, I'm really sorry. I think a should not be positive. Sorry. A should be negative and b should be positive. Okay, sorry. A should be negative and b should be positive. The answer should be C option. So like this questions are asked, and if you know how to plot the graph, it is very easy to plot and you can get your answers very quickly. Okay, so next we'll see by observing impulse response, how can we check a system is invertible or non-invertible system. Non-invertible system, invertible or non-invertible system. So earlier what we have seen xt was there, x of t was there. If it is first given to a impulse system, and if you are getting output as x of t and convolution with h of t, if you are giving, and if you are giving it to a system in which when we are getting output as again x of t, then this system was called as inverse system and this system was called as invertible system. So this we have seen earlier. But if we can generate this type of system, see, x of t and convolution with h of t we have got in the output. But if we can produce h of it, which is just inverse of this h of t. So let's see. I told you that when two signals are when two systems are in cascade, you can make a single system. So you can do such type of system that if xt is given and you have been given x of t will be given, and you have been given two system h of t and h of it, which is h of it is inverse system, and you are getting output as y of t. So here if you can bring up if you have been if you can understand that if this system is h of t convolution with h of it is the same thing which we are talking here also. H of t and h of it is there, x of t, h of t, hit and yt is there. If your h of it when convolved with h of t, if it is giving output as delta t, then you can say that this inverse system is possible and this is your invertible system. So because see, ultimately what you are aiming at, ht should be inverse of h of it should be inverse of h of t for inverse system. So we can do it that both signals when convolved, if it is giving a delta t, then it is said to be a invertible system. Okay, so from this type of system or from this type of method, you can check that by observing impulse response, you can check that system is invertible or not. See, when we are giving input as delta t, we are and for a system, and if we are taking output, we are telling that this is impulse response, because impulse input has been given, so it is a impulse response. And impulse response, whatever signal, let's suppose this has been multiplied with h of t. Impulse input was there, it is given to a system. Let's suppose this system was h of t, value and output is something. So whenever you will tell some h of t convolved with delta t, you will say it is an identity signal, so y of t will be h of t. That is why h of t is also called as impulse response. Actually y of t should be called as impulse response when delta t was input, but y of t when input is delta t, will get y of t is equal to h of t. That is why h of t is also called as impulse response, and this is h of t which have been given. Acha, whenever you have been given input as u of t, and you have been given h of t input, your system, and you are taking y of t as output, this output is called as step response, because step input has been given, so that is called as step response. What will be step response? We'll see y of t will be equal to h of t convolution with u of t. You know that any signal when convolved with u of t, it will be in same as in minus infinite to t h of t dt. This you know. So ultimately what we are getting, see, uh, if you are getting dy by dt, you will get as h of t. Okay, so ultimately what we are getting as see, let's suppose what I was telling you that let's suppose this y of t can also be see, y of t is actually general value for any input, for any type of input. If it is given to a system, you will get y of t, and y of t will be some value. But for a specific, like for a specific impulse input, we have mentioned output as h of t. Same wise as whenever we are giving input as ut, will call yt as s of t, will change the name as s of t. So here also we'll write as s of t, here also we'll write s of t will be like this, and ds by dt. So see, what I wanted to tell you that your impulse response, h of t is impulse response, that you know. Okay, h of t is impulse response. Impulse response is nothing but integration of your unit step response. In words, if I will tell you, d by dt of unit response, unit step response, I will tell you, unit step response will be equal to impulse response. In module 1 also we have seen that whenever we will do differentiation of unit step signal, you will get impulse signal only. So here also, for a unit step, for a, if you are differentiating unit step response also, we will get uh, output as impulse response only. So this you should know, because this is the value which I wanted to tell you. And the same with discrete time LTI systems also. Like in discrete time LTI system, if we are doing un minus un minus 1, so what you will get, un u of n, u of n, this value, this is u of n, है ना? And u of n minus 1 will be from 1 it will start, it will go from n is equal to 1, it will start from n is equal to 0, it will start. U of n minus 1 will be there. If we are doing minus sign, so all 1 1 1 1 value will be minus, and only this value will stay here. So what we'll get at n is equal to 0, this value, this is absolutely equal to delta of n value. So your u of n minus u of n minus 1 will be called as delta n. This we have seen in earlier also. Now what we'll see here, same for, see, for un, if we are giving input as u of n, we will get output as s of n. Whenever we are giving input as u of n to a system, let's suppose h of n is given, so ultimately whatever output is coming, you can name it as s of n. So s of n is specific for step only, like h of n is specific for delta n. Likewise this in Hindi I will explain you. कि जैसे हम कभी डेल्टा टी को या डेल्टा एन को हम भेजते हैं इनपुट की तरह, तो हम उसका आउटपुट जो वाई एन आता है उसको एच ऑफ एन से लिख सकते हैं, क्योंकि एच ऑफ एन वो होता वैसे ही है, क्योंकि मैंने अभी आपको प्रूफ करके भी दिखाया कि y और h एक ही जैसा होता है, इसलिए अपन h लिखते हैं। तो जब कभी भी h लिखाता है हमको दिमाग में आ जाता है h बोले तो इम्पल्स इनपुट दिया होगा तो आउटपुट ये आया। वैसे ही अगर हमको कोई s ऑफ t या s ऑफ n बोलता है तो हमको समझ जाना चाहिए कि वहां पे यूनिट स्टेप दिया होगा इनपुट में, और इट इज अ यूनिट स्टेप रिस्पॉन्स। सो s u ऑफ n माइनस वन जो हम लोगों ने वी हैव रिटन ही नाउ u ऑफ n माइनस u n minus 1, we can write it as s of n minus 1, and here we can write as delta n is there, for delta n output is h of n. So this is also one most important question which you should remember, that whenever unit step response is differentiated, if in terms of time domain or in terms of discrete, you'll get output as impulse. Okay, so differentiation of unit step response will be impulse response. So this was all about module 2. I think module 2 will be over, and we'll see in module 3 we'll see Fourier series for periodic signals, and then we'll go for Fourier series extended version, that is Fourier transform for aperiodic signals later on. So I think in fourth lecture I am completing this module. In next lecture we'll go for next module, that is Fourier series. Okay, till then, tata, bye bye, see you, have a good day, Jai Hind, Jai Bharat.